Hi, this is Rjchard Sedlock. Welcome back to the Green Ninja course on climate science. This episode briefly summarizes the geography and geology of petroleum and typical exploration and extraction techniques that are used in the petroleum industry. As we discussed in episode 34, petroleum didn't become an economic energy resource until the second half of the 19th century. In North America, the first oil wells were drilled in southern Ontario in Canada, at a place that later changed its name to Petrolia. A year later, the first U.S. drilling rig was operating near Titusville, Pennsylvania. And the year after that, the world's first integrated oil company was established. Integrated meaning the same company explored, drilled, transported, and marketed the oil. The market for petroleum initially was limited to kerosene for lamps, but that was enough to trigger an oil boom in the region that lasted from about 1860 to 1900. Drillers who learned their trade here later dispersed around the planet, bringing expertise to newly exploited oil fields in the Middle East, South America, and elsewhere in the U.S. As the 20th century progressed, many more uses were found for petroleum, and reserves and markets were established globally. All right, we're going to do something fun here. I want you to pause this here in a minute, and I want you to make 3 lists. Just get a scrap of paper. Obviously, I'm not going to collect this. I want you to put 5 countries in each list. The first list, on the left, would show countries that have produced the most oil to date. In other words, since 1860. The middle list will show countries that currently, this would be in 2011, extract the most oil. I say 2011 because that's the year for which data are available, the latest year. And then the list on the right will show countries with the largest remaining reserves of conventional oil. This doesn't include things like tar sands and oil shale and other unconventional sources. So list the countries in descending order so that your first pick is the one in which you have the most confidence. Right, so do this yourself. Don't look it up. You'll find out here shortly anyway. Just give it your best shot based on what you know just from living and reading stories and hearing news and stuff like that. All right, so jot these down. Pause me until you're ready. All right, here we go. Historically, the U.S. is the leader. It's followed by the former Soviet Union, which would be Russia plus the other republics. In the Kingdom of Saudi Arabia, so to be hip and also to save space, we can call it KSA, the Kingdom of Saudi Arabia. Iran and Venezuela. All right, now for the current rate of production. This is in 2011. KSA has occupied the top spot for many years, though the former Soviet Union pulled into a virtual temporary tie a couple of years ago. The U.S. is third, and basically tied for distant 4th and 5th places are Iran and China. So who has the largest reserves of conventional oil? KSA, Iraq, Iran, the United Arab Emirates, and Kuwait. So fortunately for the energy-addicted Americans, all of these countries are geographically, culturally, and politically close to the U.S. Well, they're all in the Middle East, of course. By the way, Canada is not listed because its high-profile reserves are not conventional oil. Instead, they're hard to process, environmentally disastrous tar sands. We'll talk about these in a later episode. So let's talk about the Middle East. It's geography time. So pause me again. You don't have to do this, but it'll be fun. Jot down the names of the bodies of water that have labeled A through E. And then also try this. Be really careful if you do this. Place a sheet of paper on your screen and show the boundaries of KSA, Iran, and Iraq to the best of your ability. Don't look at an atlas or a map. Just do the best you can on this. All right, so don't start me up again until you want to see the answers to these. All right, here we go. We'll do the bodies of water first. Everyone should have gotten the Mediterranean Sea and the Red Sea. I mean, don't tell me if you didn't, but on the others, over the years, my students' success rate have been about 40% for the Caspian Sea, 30% for the Persian Gulf, and about 1% for the Gulf of Aden. I'm not even sure if it's Aden or Aden, but anyway. Another water feature worth mentioning on this map is the Strait of Hormuz. It's been in the news a lot because Iran claims the right to blockade oil shipments through it. And that strait is the only export route by sea for oil from Saudi Arabia, Kuwait, Qatar, and the United Arab Emirates. Keep an eye on this in the near future in the news pages. The U.S. Navy's 5th Fleet is assigned to this region, and the Strait of Hormuz in particular, even though it's on the other side of the planet and not the home to any U.S. territory. Speaking of Iran, how about those country boundaries? Well, that's what they look like. Now, obviously, the details don't matter, but it's worth remembering that KSA makes up most, but not all, of the Arabian Peninsula, that Iran is a very large country in a key geographic position, and that Iraq is between those other two. Also shown here are the names of other countries, including Kuwait, the UAE, and Qatar, all of which are productive OPEC members. In fact, the area shown here contains about half of the world's petroleum reserves, and maybe as much as 60% of the world's petroleum reserves. This simplified map shows the locations of the larger oil fields in the area, which are shown as irregularly shaped solid black blotches. The largest of these, and perhaps the most important place you've never heard of, is Ghawar. Not only is it the world's largest oil field in a physical sense, it's also supplied about 65% of KSA production to date, 6% of world production to date, and 6% of current global production, all from that little sliver in the middle of the Arabian desert. And by the way, as a reminder, note how basically all of this oil production can only be economically exported through the Strait of Hormuz. Why is petroleum distribution so non-random? It's a set of fortuitous geological circumstances that are responsible. This slide shows 3 reconstructions of the global geography in the past. At top left, about 125 million years ago, the sediments that ultimately produced the oil of the Middle East were laid down in warm tropical environments along the margins of southern Asia and northwestern Africa in what geologists kind of posthumously call the Tethys Ocean. By about 65 million years ago, the Tethys Ocean between Asia and Africa had mostly disappeared as the continental masses moved closer to one another. Subduction zones were involved, and then the continents collided. The collision continued until, by about 35 million years ago, the relative positions of the modern Middle East had been established. The petroleum-bearing sedimentary rocks were twisted and broken up during that collision, trapping the oil that otherwise would have naturally oozed up to Earth's surface. Similar kinds of sedimentary rocks undoubtedly were deposited many times in Earth history in other parts of the world, but most of them weren't preserved, simply due to luck of the geological cards. Let's explicitly detail the steps that the Earth needs to follow in order to produce petroleum that could later be exploited by some clever tool-bearing species. First, we have to start with lots of source rock, such as a shale, that contains lots of organic material. In other words, dead plants or critters. We're trying to make a fossil fuel, after all. However, the organic material must also avoid being oxidized. This is an uncommon occurrence because oxygen levels in most ocean waters are high enough to easily oxidize the organic material. Second, heat the source rock to 60 to 120 degrees C if you want to produce oil, or to 120 to 220 degrees C if you want to produce natural gas. If you cook it at temperatures above 220 C, the hydrocarbons will break down completely and you'll end up with nothing but divorced hydrogen and carbon atoms. This heating will take millions of years. Third, make sure that your source rock, the one that you're heating to produce the petroleum, is overlain by a reservoir rock. The petroleum will rise because of its low density. It's lower density than the surrounding rock. So you need a porous and preferably permeable rock to hold that stuff. I'll talk more about what porous and permeable mean in just a moment. Finally, make sure that the reservoir rock has a suitable trap, a subsurface geological structure that will hold or trap the petroleum in the reservoir rock and prevent it from escaping upward to the Earth's surface. So more on this in 2 moments. These cartoons of greatly magnified sedimentary rocks show pores, open spaces between the particles of a rock. Pores may contain air, gas, or liquid, such as water or oil. So the more pores a rock has, the more porous it is. The pores in the bottom cartoon are much better connected than those in the top cartoon, so the pore contents will flow much more easily. We say that these kinds of rocks on the bottom are more permeable. More permeable rocks make great reservoir rocks. Here's another cartoon, this time showing a vertical slice through Earth's crust and several traps that can accumulate petroleum or water if they are available. The rock layers are color-coded according to the contents of their pore spaces. Yellow rocks just have air in their pore spaces. Red ones contain natural gas. Green ones contain oil, and the blue ones contain water, of course. Now, the nature of the particular traps doesn't matter for our purposes here, although budding geologists get lots of training about how to find and recognize and interpret them. An important point is that any given trap is likely to contain more than one material in the pore spaces of the rocks. For example, look at the anticline at the left, the sort of upward bulge of the layers. It contains both oil and water in its pore spaces. Because the oil has a lower density than the water, it moved farther up within the reservoir, and rocks with oil in the pore spaces lie above rocks with water in the pore spaces. Above the salt diap here at the right, pore spaces contain not only oil and water, but also natural gas. Because the gas has a lower density than either the oil or the water, it rises to the top of the reservoir, above the oil-bearing pore spaces, which are above the water-bearing pore spaces. Petroleum companies employ geologists to explore for suitable reservoirs and traps. Even if they find a reservoir, that was step 3 from a couple slides ago, that has an effective trap, that was step 4, chances are good that it'll be a dry well because the source rock wasn't appropriate, that was step 1, or because the source rocks were heated too little or too much, that was step 2. Still, you have to try if you're going to find anything. Exploration and production steps always start with exploration. A few oil fields were found through dumb luck. Think Jed in the opening of the 1960s TV series The Beverly Hillbillies. But almost all require hard work. In the early days, exploration took the form of geologic mapping done by footsore geologists. By the 1930s, companies were using geophysical equipment to explore the subsurface remotely, from trucks or ships at Earth's surface. By the 1990s, they'd added powerful computing facilities, which gave geologists the tools to track down ever smaller and harder to find prospects. When the geologist, or more typically the team of geologists, has identified a prospect, it's recommended to management, which considers the recommendation and may ultimately authorize the drilling of a test well. If petroleum is present and is trapped and thus under pressure, it will rise naturally to the surface without the need for pumping. Many of the oil wells of the late 1800s were like this. Free-flowing petroleum in what geologists term the primary recovery phase of production. Gas, natural gas that's released during the extraction of liquid petroleum is valuable, but trapping and processing it requires technical savvy and equipment that wasn't developed until the middle of the 20th century. So for many decades, natural gas was simply ignited at the wellhead and flared off into the atmosphere, adding lots of CO2 to the atmosphere but supplying no energy to humanity. Primary recovery at a well may last for a few weeks or several months, or in a few cases even several years. Sooner or later, though, the internal pressure in the reservoir drops, so the flow of petroleum declines, and the operators will use secondary recovery techniques to obtain more petroleum. The most common secondary technique is to inject water or gas into injection wells. As the water or gas is forced into pore spaces, it raises the pressure again and sweeps the petroleum in front of it as it advances. In a typical layout, several injection wells would surround a production well that sucks up the advancing petroleum, plus progressively larger amounts of the injected water and gas, which are useless. In fact, the injected water, it's worse than useless. It usually results in a set of predictable problems: corrosion, scaling, the need for treatment before disposing of the pumped out water, costly processing, and parts replacement. Still, the profit from the additional petroleum makes this worthwhile in many cases. When the rate of secondary recovery drops enough, operators may shut down the well. Alternatively, they may pursue tertiary recovery techniques to obtain even more petroleum. Now, the goal of most tertiary recovery operations is to reduce the viscosity of the oil so that it flows more easily into the production well. This is done by heating the oil, typically by injecting steam. Realize that steam requires a lot of energy to heat the water that hot. Other tertiary techniques include flooding the system with CO2 or adding detergents or microbes that break down the long organic hydrocarbon molecules. These techniques are really expensive, and so they're used only if the price of oil is high enough, the market price, so that they can recover their investment and make a profit. This graph shows the production history of a particular oil field in the North Sea, which is the body of water between Norway and the UK. The field was discovered in the late 1950s. The rate of primary production rapidly increased until about 1965, when it peaked and started to decline similarly rapidly. In the late 1980s, operators began secondary techniques that successfully increased the production, the yellow and red areas. But by 1995, production started to drop precipitously. So in the late 90s, operators began expensive tertiary techniques that successfully increased production again. However, the prospects for future recovery are very low because so much of the original petroleum has already been extracted. Around the globe, the easy-to-find and easy-to-extract petroleum has been found and extracted. This low-hanging fruit, such as the gusher at the lower left, is gone. It's all been picked. Lots of petroleum remains, but we've extracted so much by now that this remainder will be progressively more difficult and more expensive to extract. And that's the end of episode 35.